So my research paper was about the fundamentals of programming with robot operating system, and I'm Harshini Srinath, and my mentor is Samuel Lenscraft, and he is a PhD student at Dartmouth Reality and Robotics Lab. So some stuff about me. I'm a junior at American High School, which is just a school in Fremont, California, and I'm interested in computer science and mechanical engineering. I love programming and working with artificial intelligence and robots in general. And some other things are that I'm a captain of a robotics team, and I recently programmed an AI car to navigate around a track autonomously. So those are some things that I find interesting. And now moving on to my topic, what is a robot operating system? So robot operating systems are also known as ROS, and this has a variety of software libraries and tools that allow users to write algorithms for their robotics applications. It just makes it easier to write commands and to run code. And in ROS, there are processes which are called nodes, and nodes just carry out some basic tasks based on what the user wants the node to do. And nodes communicate with each other by using messages that pass through topics, and nodes can publish messages to a topic and can subscribe to a topic to receive other messages. So when they publish to a topic, they send their data to another node, and when they subscribe to a topic, they get data from the topic. And a bit more about ROS is that nodes can be written in either Python or C++, which are just two different programming languages. Users can also use different languages by installing other libraries like ROSBridge. And in addition to a large amount of libraries, ROS also has a large assortment of packages, which is what makes it very useful, and which is why a lot of programmers choose to use this when working with their robots. For instance, there are some packages that allow a remote control feature to be used for their robotics applications. And there's also a simultaneous localization and mapping, SLAM feature, which can be used to make applications. And in these two pictures on the left, those are just some SLAM algorithms that produce some maps that the robot can use. Okay, and now moving on to my specific topic. So the goal of my research paper was to explore the process behind installing Ubuntu 18.04 and ROS Melodic and writing my own Python publisher and subscriber nodes. So the reason why I chose this was because whenever programmers are writing any pieces of code, they often run into errors when related to downloading packages or libraries, so they have to troubleshoot. And if this troubleshooting is not done correctly, the goal of the user might not end up working. So I also want to see how these errors would affect me and my goal of creating my own nodes that would communicate with each other. So now for the introduction, along with talking about the installation of libraries, Ubuntu, and the creation of the nodes itself, my paper also discusses and evaluates the errors that arise when installing these libraries and writing algorithms, provides an in-depth explanation of each step of the installation and its purpose so that people know why you write a piece of code and what the purpose of a certain library is. And this is just to help people understand how to get started with ROS, since online there's many different resources that differ based on your computer setup, and it's kind of hard just getting into ROS to figure it out from online. And the reason why ROS is pretty important, like I mentioned in the previous slide, is because the algorithms that you write with ROS can be reused for different robot applications. So it's easier to test the same function over many different projects. And additionally, it helps developers simulate their robot in environments before they actually test it, so they can get more data and they can see how their robot would interact with different things. And now moving on to methods. So the first part was installing a virtual box. A virtual box just allows users to run multiple operating systems on a single host, which is just their physical computer. A virtual box makes it easier for users since they can run virtual machines on their computer without having to reinstall their operating system or erasing any of their files. So for that reason, I downloaded the Oracle VirtualBox because I did not want to make any changes to my Windows operating system. And that's actually what I'm using right now. And in the picture on the left, you can see my VirtualBox being open, and then the name, which is just Ubuntu 18.04, and then the operating system, how much memory I put in for the system and actually for the storage, and then some other options and where everything's located. And then Ubuntu 18.4. So I downloaded this version, even though it's older, because it's actually the only version compatible with ROS Melodic. There's some more recent versions like 22.04, but this is the only version which actually works for writing code with ROS. So that's why I downloaded it. And then I created an empty virtual machine in the VirtualBox. And the options I selected were a virtual hard disk, because again, I didn't want to make any changes to my computer's hard disk, and dynamically allotted storage, so that as I used up more space and my hard drive file became bigger, there would be more space available on my virtual machine, so I could continue coding and using other features. And the last step for the Ubuntu installation was to select my virtual optical disk file. And this is just where the Ubuntu would be located. So in the first step where I downloaded the Ubuntu 18.04, there was a .iso file, which I ended up using as my location. Then I just restarted my Ubuntu, and then the wizard installation popped up. And once it was completed, then the picture on the left comes up, which is just the basic graphical user interface. And then you can click on different things like the terminal to write code, text editor, you can also run code through there. And then there's Firefox if you want to search things up, and etc. And then ROS Melodic, which is what the whole topic of this paper is about. So to do that, I first have to set up my source.list to accept packages from the ROS website, because I was using various things such as like the full like simulations for 2D and 3D and 2D and 3D perception. So that came from ROS website. So I had to make sure that that was set up properly. And then afterwards, I installed my keys, which was a curl. And then this just verified that packages were really what they said to be, but comparing the signatures of the binary ROS. And then I updated my Debian packages by running like sudo apt and get upgrade. And then the Debian packages come in two different types of packages, which are binary and source packages. And both of them use dependencies which are needed for the nodes to actually function. You have to run some of the dependencies. And the important thing about dependencies is if like package X depends on package Y, you can't run package Y before package X, or else there would be an error and then it would stop the download. So that's how the nodes work. And then I installed the full desktop ROS because it had more features, including simulations and 2D and 3D perception. Next step was to create a Catkin workspace. You can basically call this whatever you want, but just a workspace where your folders will go into. So I made a new directory and I put a path for Catkin underscore workspace / source. And this just created folders in a different directory than what I used for my ROS installation. So it's easier to navigate through and I wouldn't get confused when I was referring to everything. And then I changed directories into just the Catkin workspace. So when I made folders, it would just be in that specific directory. Again, this just makes it easier when navigating and running code. So you can just put everything in that directory instead of having it in like the base directory where all the installations happened. And then I ran the command catkin underscore make, and this just makes different folders, and it made the C make lists.txt link in the source folder. And then there were also build and develop folders. And these folders had setup.sh files. And these files are important because if the user wants to make the Catkin workspace work in any different way, they can just open up the setup files, then change it in the text editor, save it, and then it will work how they want it to. Like for instance, users could change the code so that the terminal will just automatically pop up whenever Ubuntu's open, and they can just do that by changing code in the text editor. And on the picture on the left, you can see my Catkin workspace folder and then 3 folders: build, develop, and source. And then Catkin packages. I created a package called beginners underscore tutorials, and this depended on standard messages, ROSPy, and ROSCPP. So I made sure to install ROS-PY and ROS-CPP first to make sure that the beginner tutorials would actually work for my nodes. And then I ran Catkin _make again, which I talked about in the previous slide, just to make more folders. So like I just said, it created build, devel, and source folders inside of beginners tutorials. And the beginners tutorials folder was inside of my source folder over here. So it was in there. So that's how I accessed it. And finally, to the publisher and subscriber nodes, I first created a scripts directory for my code. And I just changed directories into the scripts by doing cd scripts. And afterwards, I wrote the code out for publisher. And basically what this code did is it published hello world to the chatter topic by using strings, which are what the standard messages are. And then the subscriber was similar in code to the publisher, and it just subscribed to the chatter topic. So whenever the subscriber got any new messages, there was a callback feature that was invoked with the message as the argument. So that way the publisher would be printing hello world repeatedly, and the time would pop up too. And then when the subscriber saw that, it would also print out hello world. And if I changed my node so that it would change the code, like not just hello world all the times, then the subscriber would just use the most recent message it sees and print that out. And also, to make everything work, one of the most important steps was to run ROS-core in a separate terminal. So in total, I had 3 different terminals open, one for ROS-core, one for the publisher, and one for the subscriber. And then for my discussion, like I expected, there were many errors. For instance, I once mistyped the command, so I was in the wrong directory. So when I tried to run a command, it was saying that that was not found because there was no installations in the directory relating to the command. So that's something important. Also, sourcing the environment. So the command to do this would be source/ops/ros/melodic/setup.bash. And this just changes the environment of the shell that you are currently in. And the purpose of this is to run the scripts that are contained in the file. And it sets up environmental variables for ROS so that ROS can easily find like libraries and packages. And this is important before running any code to make sure that you source your environment, or else there will be an error like something's not found or this command is not available. So that's the importance of sourcing your environment. And the last error was memory and storage space. The first time I installed my VirtualBox, I put only 10 gigabytes of memory. So when I actually opened everything up and tried to use Firefox, it would not load correctly. So the next time I had to put more memory space, like I think I put 5,000 gigabytes. And for storage space, you need more storage space, or else your terminal, it will give you an error saying that there's not enough storage space and you won't be able to write more code or run any more commands. And my conclusion was that I was able to install Ubuntu 18.04 and ROS Melodic, and I wrote a publisher and subscriber node that were able to communicate with each other. Like I said in the previous slide, some of my errors were not having enough storage space, and I had to source my environment each time I ran a new command to make sure that it actually worked and it could find where I was, which directory I was in. And some of the next steps would be to use actual data from a robot. I could use the ROS-bag command to play a file, and then I could write custom nodes that listen to the images from the file, so that when it hears the image, then it can print out the image, the data in the image and the time. And then and then when you do that, it's easier for the publisher and the subscriber node to communicate with each other with this data. And then a special thanks, a big thank you to Sam, who's my mentor, for always replying to my emails and answering my questions to help me with troubleshooting in the initial installation phase and get on Zoom meetings to figure things out. I learned so much from this opportunity and got to strengthen my programming skills. I couldn't have asked for a better mentor. And also a big thank you to the Talaria program managers for setting up this program. It was extremely helpful and I got to learn so much. Thank you for listening.